Nuclear reactors are among the most sophisticated machines ever created. The complex engineering required to design and build them, combined with the high temperatures produced in their cores, means they have to be perfectly calibrated and meticulously monitored. And until recently, the designers of nuclear facilities have had to rely on dated computer simulations to anticipate how a new reactor might behave in the real world. Once these reactors are in service, teams of skilled operators use data collected from thousands of sensors to verify that every system remains in harmony. When anomalies are detected, technicians have to be dispatched on carefully coordinated schedules to make repairs. This combination of careful planning and data-driven decision-making has been key to safely operating nuclear facilities for decades. But these measures are also extremely expensive, tedious, and rely heavily on human decision-making. Fortunately, a new generation of nuclear reactors is being developed in parallel with artificial intelligence systems, called digital twins, that we and our research collaborators expect will make their design and operation safer, more efficient, and more cost-effective than ever before. As the name implies, these systems rely on exact digital replicas to optimize real-world physical systems. And by 2029, we expect that X-Energy's Xe-100 will be the first reactor designed to bring this burgeoning technology to a commercial nuclear power system. Already used in the world's most technologically advanced sectors of research and manufacturing, digital twins use data collected from their real-life counterparts and simulate the conditions of the real world to monitor performance and even recommend improvements in real time. Imagine testing the limits of a new car concept before ever producing a prototype. By accurately simulating the car running at top speed in extreme driving conditions, engineers could pinpoint exactly which systems fail under what circumstances and then use artificial intelligence to recommend improvements to the design. This is the type of scenario that digital twin technology makes possible without safety risk or financial burden. Originally developed by NASA, the first digital twins were used to model spacecraft in the early 2000s. The success of these first projects led to the near immediate adoption by private industry, from healthcare to aviation. Now, clean energy companies like X-Energy are pioneering the use of digital twins for the design and operation of advanced nuclear reactors. Whereas a traditional simulation may be limited to studying a single scenario or set of data at a time, a digital twin can study thousands of processes simultaneously while passing its findings back into the physical system to make improvements. This use of real-time data on a massive scale is what makes digital twin technology so transformative. A digital twin connected to an advanced nuclear facility can mirror the entire system and analyze the health of individual components in real time to recommend corrective action only when necessary. This means that reactor components can be used longer with fewer operators and leave less room for human error. Another key benefit of building a digital twin is the ability to use machine learning to make highly accurate predictions about the future state of a reactor, thus allowing the digital twin to recommend improvements before a problem ever presents itself. As you may know, machine learning is a subset of artificial intelligence that trains computers to recognize complex patterns in massive amounts of data. It's the same technology that powers facial and voice recognition software and helps our navigation apps predict traffic patterns to recommend driving routes. By being digitally connected to a central support center, each reactor on the network will feed its data back into many machine learning algorithms. We expect that this approach will dramatically increase the accuracy of digital twins' AI-powered prediction capacities, and this new generation of reactors will grow smarter together. This cooperative network of smart reactors is what is being set into motion through the development of Xe-100's first digital twin. Running high-fidelity simulations, the technology has already provided critical insights to the design of reactor systems and operational procedures. Because this twin is a mock-up of an Xe-100 facility, it can be used to test important parameters without consequence, like how many operators are needed to manage the plant, or how the reactor will respond to operator error or varying environmental conditions. These simulations are expected to help train the next generation of operators and technicians in the safety of virtual reality. This use of VR is far from trivial and won't be limited to training programs. These interfaces will also provide a valuable tool for engineers in the field, allowing them to virtually step inside a fully operational reactor core, gaining previously unimaginable insights into potential vulnerabilities and solutions without ever actually leaving their offices. We expect X-Energy's Xe-100 to represent a huge leap forward in the production of clean energy, and the development of the digital twin with our research partners will empower this groundbreaking reactor to continuously grow safer, more efficient, and more cost-effective for decades to come. Welcome to the age of the smart reactor.